Hello, my name is Jan Gelkowski, and I am doing here a retake of a presentation which I made to the Walpole Greens in Walpole, Massachusetts on Monday evening, the 9th of November. I'm doing this because not everybody was able to attend that meeting and it wasn't recorded. At the end of the presentation, I will attempt to recall some of the questions that were asked and my answers. And actually, some of the answers that I have now are better than that because I was able to look some things up. Uh, but this is a much more informal setting. It'll probably run a little bit longer than the actual presentation on Monday evening. I also am accompanied by our three cats. One is in my lap that you can't see very well. His name is Samwise. Dusty is over here to my right on the chair. And one's circling around the room someplace. That's Darla, the black one. So that's it. So let's get going here, and we'll go get underway. Okay. All right. So thanks to the Walpole Greens for hosting this meeting and inviting me to speak. My name is Jan Galkowski, and the Walpole Greens actually has, if you're familiar with them, a more complete bio for me that you're welcome to check. I also have a blog online. It's at the URL 667-per-cm.net, 667 per cm.net with dashes in between. I invite you to check that out. Anyway, I'm a resident of Norfolk County. I live in Westwood. I have a master's in electrical engineering and computer science from MIT, specializing in artificial intelligence that was awarded in 1976. I've done additional graduate work in mathematics, signal processing, numerical linear algebra, geology, and additional coursework in biology and geophysics. I have a bachelor's in physics, and in my undergraduate days, I took botany as well. Okay, choices. So what's this about? The major subject at hand is a proposed project in Norfolk County, proposed by the county itself on land that they own for a 6-megawatt solar array, solar farm, divided into two parts, a 5-megawatt section on North Street and a 1-megawatt off Fisher Street. And I'm trying to set the biological and climate context of this, and the context of energy policy in Massachusetts, as well as what's going to be happening with technology, particularly photovoltaic technology in the years to come. So what this is about is, from one way of looking at it, and I think a synoptic way, is about controlling your economic future, quite possibly your own, but certainly that of Walpole and Norfolk County. There are inexorable economic changes coming regarding the cost of energy. These changes are driven primarily by technological innovation, not by concern about climate disruption, and they will come no matter what federal or other policies are. To the degree businesses and households are aligned with those changes and aligned now, they'll have some control over how this plays out. Otherwise, they won't. And in those cases, no government, no activist group, in my opinion, will be able to push back against the economic onslaught, because to do so would forego economies that no serious business or household is going to be able to ignore. Now, I need to try to convince you that this hyperbolic hypothesis is true. So this is something called the Keeling Curve. It shows the concentration of carbon dioxide, or CO2, in atmosphere. And here it's shown as a series of monthly averages. That's what each of these black dots are. This measurement is taken at Mauna Loa Observatory in Hawaii, but the same chemical procedure is done a few times a day at each of a dozen and a half stations around the world, including Antarctica. Now this is also measured using satellites. This was developed, the chemical procedure for doing this, which is not easy. I mean, the technology of doing it is not easy, was developed by Dr. Charles David Keeling and continued by many, including his son, Dr. Ralph Keeling. The concentration is currently about 450 parts per million, and that is humanity's legacy. And I will talk about that briefly a little bit later. The major point of showing this and pointing this out to you is I wanted to show this sawtooth pattern. That's the feature that's highly pertinent to this talk. Now, I don't have a close-up of that in this slide deck, but take my word for it that this zigzag has a low in October and a high in April, May. And these correspond roughly to the beginning of autumn in Northern Hemisphere and the spring Northern Hemisphere. And what the interpretation of this is that this is interpreted to be the effects of the Northern Hemisphere forests, all of them. And beginning with the growth in the spring, they expand and they draw down carbon dioxide in the atmosphere up through October, and where leaves fall off and the forests go quiet and they yield back all the CO2 that they've captured. Note the climb in the concentration over time from 1958 to the present. And note how small the contribution is from all the northern forests. So suppose the number of trees in their attending ecosystems were doubled. Yes, the sawtooth swings would be roughly twice as big in amplitude, but they'd be, you know, compression and relaxation. Or extension and relaxation, however you want to look at it. There is some increase in the amount of what's called net primary productivity in these forests, about 1% per year, that these are bigger. But in comparison to the amount of emissions driving the carbon dioxide in the atmosphere, it's tiny. And also the other thing is that, and again, this is not a climate talk, but should temperature increase, it's not clear that that 1% per year climb in net primary productivity will continue. So the point is that if you're talking about, that's all in northern temperature forest, by the way. It's northern hemisphere temperate forest because there's just no land in the southern hemisphere that supports that. There's some, but not compared to the northern hemisphere. And if you were able to plant like a doubling of trees instantaneously, sure, there'd be a downturn in slope of the curve, although it would continue to go off, and that downturn would persist. It is calculated about 60 years, and then it would continue to climb as it does now, and assuming carbon dioxide emissions didn't increase. And the other thing to note is that there are no inflection points corresponding to political changes anywhere. There's a slight change here in the amount of emissions in the atmosphere, but that turns out that has to do nothing with political changes. That's a natural change. They won't go into it. It would be too complicated to talk about, but you can contact me if you want to know more. But you know, all through the George H.W. Bush administration, all through Bill Clinton, all through George W. Bush, all through Barack Obama, and all through Donald Trump, this uptick of the slope has just continued. Now, of course, the reason why those emissions are going up is because we're emitting them into the atmosphere, and the principal source of emissions is combustion of fossil fuels. There's also a chunk that comes from making clinker, which is a component of cement, and there's a chunk that comes from agriculture. And when I say from agriculture, I don't mean tractors or processing or transport, just agriculture. Rice cultivation, for example, produces a lot of methane, and methane eventually decomposes into carbon dioxide. Now, we know the sources of all this carbon dioxide because of isotopic chemistry and the isotopic chemistry of fossil fuels themselves. But this slide in particular shows a little bit something different. This shows the life cycle emissions for various kinds of energy sources. Now, what a life cycle emission means is it means like if you take a natural gas combined cycle plant, not only do you have the natural gas that's being burned to generate heat and steam and then electricity, but you also have the construction of the plant itself, including everything that goes into it, the steel and the concrete and everything else. And then you have the piping, the pipes, if the natural gas is brought there by pipes, or the trucks with LNG, all the way out from the sources, and whatever the cleansing is done, and then finally the mining or extraction of the natural gas. In the case of fracking, that extraction involves injecting water with various things, chemicals mixed into it at high pressures, which of course requires energy, and so forth. And then along the way, in the case of natural gas, since that's what I was talking about, there are incidental emissions of methane, and methane is a potent greenhouse gas that in any event decomposes down into carbon dioxide. So that's a life cycle of emission. So it's not just the point emission of burning a certain amount, certain cubic feet of natural gas. It's also the whole line all the way back to where it comes from. Similar things can be talked about oil, coal, lignite. In fact, life cycles are not, emissions are not limited to energy production. Basically, any product that we use has a life cycle. So, for example, if you compare plastic bags with paper bags purely on the basis of life cycle emissions, the paper bags are much worse. Paper is much worse because not only do you cut down trees, even if they're farmed for it, but there's an awful lot of processing that needs to be done to that raw wood to turn it into paper, including getting rid of the lignin and a bunch of stuff. And then naturally those chemicals that are used for that are themselves need to be extracted and produced and so forth. So there's a lot. And then finally, paper bags are heavier. So if you have to take paper bags to your grocery store, you need more trucks because they weigh a lot compared to plastic. Plastic, on the other hand, although it's from petroleum and that kind of thing, is actually, it's very lightweight and it can be made very easily. So there you go. There's a life cycle emission that's perhaps a little counterintuitive. The other thing is that, to contrast, of course, is the life cycle emission of wind power and solar and nuclear and hydropower, which is essentially negligible compared to the others in this case. And just wanted to show that comparison. The other thing that it does is, because if you go on the web and you read about like wind power in particular, for some reason, people have this notion that the upstream emissions of wind power, which would make the turbines and the motors and rotors and that kind of stuff, is high, and that's just not true. And this demonstrates it. One last point before I leave the slide: there's this other stuff here called nitrous oxide, N2O, and when you talk about greenhouse gases, we usually talk about carbon-based greenhouse gases, and you talk about forests, you talk about carbon-based greenhouse gases like CO2 that's captured in things. Nitrous oxide is produced principally in the world by, although not exclusively, principally by fertilizer. So if you fertilize crops, when the fertilizer decomposes and things, it releases nitrous oxide. Nitrous oxide is a centennial greenhouse gas. What that means is, that's technical speak for it's worse than methane. And there have been proposals, for example, to try to address climate change by massive planting of forests, and they want to do it fast, so they propose using fertilizer, and that has to be done carefully. That's not necessarily a win. Well, burning of fossil fuels has other consequences besides, this inexorable rise of carbon dioxide in the atmosphere and the associated climate change, which, as I said, I'm not going to address today, which involves warming and stuff like that. I've done climate talks before. I taught a whole course about this in summer on Zoom in summer of 2019. Zoom because it was convenient. I can do that again. But in any case, we'll not talk about that here. Fossil fuel emissions by themselves can be harmful to ecosystems and people. Here's a case of a coal burning plant that has been there for a while, at least 40 years, and it's taken out a whole forest about it. In fact, if you old piping systems for natural gas tend to develop a lot of leaks. Boston has a lot of leaks, for example, and one of the tells that it has leaks is the natural gas will kill trees around the leak and vegetation. The other thing about, irrespective of rising temperatures, if you raise temperatures, if you raise carbon dioxide in the atmosphere high enough, it causes ocean acidification. So if you get up to the realm of like 1,000 parts per million of atmospheric concentrations, and you sit around at that point for 2-3 dozen years, the ocean equilibrates with it, and the ocean becomes acidic. And it's concerned, and there's tangible evidence for this, that might be enough to kill off most of the fish in the oceans. And just point out that 1 to 2 billion people on the planet get their primary source of protein from the oceans and shellfish and such. So that has a direct consequence, irrespective of effects on storms, droughts, and temperatures, and ice caps. Now, as I mentioned, carbon dioxide is our legacy. And I find when I talk to people, if I talk to people about climate, a lot of them don't appreciate how long lived carbon dioxide is. I think they think of it as being like ozone or maybe DDT. DDT hangs around a long time, but not like carbon dioxide. Let me just talk about the slide for a second. What this shows is it shows a number of calculations, hence the number of curves, of the following experiment. Suppose you put a pulse of carbon dioxide into the atmosphere all at once. The carbon dioxide started out in the atmosphere at 288 parts per million. That's down way down here. And suppose if you essentially put a pulse of 480 parts per million all at once. And what I mean by all at once is within 100 years. That's about right. It could be 200 years if you want. But in any case, that would bring the carbon dioxide in the atmosphere up to about 750. Now, actually, it turns out it's a little bit more complicated than that, because for every, for every 10 units of carbon dioxide that we emit, only about 6 to 7 of those units actually end up being in the atmosphere. Some of them mix into oceans pretty quickly, in other places, to some extent in soil, but mostly oceans. And so a pulse of 480 parts per million is actually, whatever that is, divided by 0.6 if you want. And so it's bigger. But anyhow, it's estimated that if we continue emitting at the rate that we are today, we'll have that atmospheric concentration about 50 years. Now, as I said, the actual concentration is measured at 415 parts per million. But in fact, that doesn't count all like the methane and stuff that's in the atmosphere. That will eventually degrade and become carbon dioxide. So in a way, it's carbon dioxide in waiting. And so if you threw that into the mix, you would actually put us at 500 parts per million. So you see, it's not that far away. We're almost 100 parts per million higher than what it seems from our measurements. But note, this experiment, you throw all that 480 parts per million in the atmosphere all at once, and then you stop. You stop cold turkey. You emit nothing more. And nothing from fossil fuels, nothing from agriculture, nothing from cement. And what happens? What happens is it starts to come down, and after 200 years, you've dropped about 200 parts per million. So, and that first drawdown is largely due to the fact that the oceans are now equilibrating with that thing. The oceans will equilibrate and take some of that carbon dioxide in, but it takes them time to do so. And so that's about 200 years. And then, after 600 years, you're back to the present concentration. But you never get down to the original concentration of carbon dioxide. As a matter of fact, you never get to, except for a couple of calculations, you never get to 350 parts per million, which is a target that some climate scientists think is what we should aspire to. That won't happen for 10,000 years. Moreover, if you were to emit more than, if you didn't stop cold turkey, and if you were to emit more than that 480 parts per million kept going, if you're up to 1,000 parts per million or something, this whole set of calculations would just shift up accordingly. I mean, it would just shift up. So the time required to get down to a more reasonable concentration of parts per minute would be long. Also, that stuff that goes into the oceans, it hasn't gone away. It's just that the oceans are in equilibrium. They're a solution. They're in equilibrium with the atmosphere. So if you had a magic machine that you invented with technology down the road somehow that was able to cheaply extract carbon dioxide from the atmosphere and put it someplace where it couldn't get out anymore, and you drew down like 100 parts per million from atmosphere for doing that, what would happen is that you'd get 50 parts per million back out of the oceans. So to draw down, actually, it's not quite true. You'd get 40 parts per million back from the oceans. So basically, to draw down 100 parts per million from the atmosphere and to keep it there, you actually have to draw down something like that's not right. Sorry, 125 parts per million, right? From the atmosphere to do that, and so that's why I say, that looks like the first 200 years looks like that looks really good, but that's misleading because it hasn't gone out of the climate system. It won't go out of the climate system it'll start to get out of the oceans and be scrubbed from the oceans after about 1,000 years, but it's still there. And if something really bad is happening with the atmosphere, with concentration being so high, and you really get desperate to do that, the work that you have is bigger than it seems. I didn't mention this in the other talk. I mentioned in passing, there actually are technologies that are being, and you may have heard about them in news or science magazine and stuff like that, that are being considered for drawing down carbon dioxide from atmosphere. And I mentioned before the idea of people who want to go crazy planting forests all over the place. But two quick points before I go on. One, those technologies exist, but they're horrifically expensive. Yeah, I did a calculation that's documented in my blog in a couple of places. If you were able to improve the cost per ton of CO2 removed from the atmosphere by a factor, it's currently like $600 a ton, roughly, of CO2. If you're able to bring that down just below $100 a ton, that's a six-fold improvement. That's not bad for technologies. The price to draw down carbon dioxide, 70 parts per million in our atmosphere, is like, I think the number is like 14 times the gross world product in 2014. It's enormous. It's not cheap enough. You'd have to bring the price of extracting CO2 down from the atmosphere down to $1, so 600 times. And then it starts to get into the realm of, yeah, if you really put a lot of money into this, several $1 trillion, or I think I calculated like 20 channel projects. The channel is the thing underneath the from England to France, under the English Channel, although the French don't like to call it that. 20 of those projects, you could do something at $1 per ton, but we're a long way away from that. Okay. Oh yeah, and the forests. Yeah, so the forests, I told you about nitrous oxide before. The forests are also a little tricky because forests have an albedo, which is darker than like solar panels. So, or it's a little darker than cement. So what that means is that albedo basically is how much of the light coming in from the sun is reflected back into space. And to the degree that light is not reflected back, then it warms the surface of the earth and contributes to warming. So by planting a bunch of forests in areas that are either covered by cement or are arid regions, now you're actually darkening the planet, and doing that warms it. So you may be planting forests to draw down carbon dioxide so that you don't warm things, but you're warming it directly by changing the albedo of the planet. There's proposal, for example, there's a plant called geophysical, which actually does really well in arid regions, tropical regions, and it doesn't get eaten by anything because it's really toxic. There's a proposal. Matter of fact, there's one or two companies who propose planting this stuff at scale in arid regions of the planet, like the Saudi Arabian desert and stuff, and potentially harvesting the oil from it for biofuel and stuff. But nonetheless, and apart from what it would do to the local ecosystems, the other problem then this is actually being calculated out. The other problem with doing that with Jatropha is that if it's at a big enough scale, it will literally change the climate on the Arabian Peninsula because it will hold much more moisture being a plant. And eventually, it probably is going to change it so much that it will actually kill itself off because other things will start to grow there. Maybe as good as Jatropha, maybe not. But in any case, that on top of the albedo change compared to the desert is something that has to use the calculation. This isn't limited to forests, by the way. And this is why if you start to try to manage the earth at scale, you have to think about these things. So in the case of wind energy, this study is something else that's been done. If you were to build out basically along the East Coast of the United States, let's say 90% of the wind turbine energy that's possible to be harvested there, because I don't know how you get that last 10%. But anyway, if you did that, there is a calculation that's been done that shows that you would decrease the amount of wind energy available to storms by a significant amount, like 20% or something. I'm just pulling that out of the air. I think it's about 15–20%. So engineering at this scale, no matter what you do, is going to have consequences that you have to essentially master. So I said that carbon dioxide is our legacy, and this is why, is because, civilizations build pyramids, and that's supposed to be their legacy and the things like that. Carbon dioxide is going to be around such a long time that this is our legacy. We're massively changing the earth. Indeed, it's been speculated that if you had intelligent life elsewhere, this would be our signal of having so-called intelligent life on the planet, because there's no natural process that puts up CO2 this quickly. You can have mass extinctions like the Permian do it reasonably quickly over a series of centuries, but not like this. So the message there is natural systems don't sequester carbon quickly. Now, we're going to talk about tons of carbon here, and we were just talking about tons of CO2. And this is just chemistry. And the reason is because carbon dioxide is what trees and things get used to get carbon. The CO2 goes into the trees, they take out the carbon and make food in the process, and so on. So yeah, basically I'll be switching between units, and it can get a little confusing. Turns out that a molecule of carbon dioxide weighs 44 units. 12 of those units is a carbon atom, and the other 32 are 2 oxygen atoms. And so if you want to go from carbon dioxide weight to include the carbon contained in that carbon dioxide, you multiply by 0.273. And if you go the other way, from carbon to the equivalent carbon dioxide, if it's burned and that kind of stuff, you multiply by 3.67. And that's just the way it goes. So since we're talking about sequestering carbon in trees and such, I'm going to be talking about carbon now, not CO2 per se. So humanity emits about 15 billion tons of carbon each year. Of that, 2 to 3 billion is emitted from agriculture, and about 2.2 is just from clinker for cement. All natural processes on the planet, including forests, soils, oceans, grab 2 billion tons of carbon per year. So you see there's this big imbalance, and that's why the Keeling Curve goes up. By the way, 15 billion tons of carbon each year is 55 billion tons of carbon dioxide. That's a lot of stuff. Let's see. Right. By the way, the other thing to say is some of that natural processes is not just forests. It's also plankton in the oceans. And the thing about them is they don't have natural cycles like the forests do. So they don't have this up and down, and they don't show up in an up and down, but they're there. But obviously, they're not offsetting the emissions of carbon dioxide in the atmosphere on the Keeling curve. Otherwise, it wouldn't be going up. All right, so let's look at that sequestration of carbon in forests, in temperate forests. It turns out that the forests that are really good at sequestering carbon are so-called old growth forests. And these are about 180 to 200 years old, mostly undisturbed, predominantly undisturbed. We have not learned, except during the last 15 years or so, how delicate this process is. The Harvard forest, which is an experimental forest in Harvard, Massachusetts, is monitored for the amount of carbon dioxide coming into it and going out of it and such. And they've tracked in real time some of the changes. So, for example, they have a hickory subforest there, and there is a pest called a woody adelgid that has infected that forest. In fact, it's not that rare for the Harvard forest or hickory. We have it on some of our trees here in Westwood, on our own personal property, that it had to be treated. But in any case, the woolly adelgid was found that in the subforest that was hickory to completely change the chemistry of that subforest so that those hickory trees are now a carbon source, no longer sequestering carbon. And that's kind of surprising. And when the paper came out, everybody was kind of like, ooh, because it shows how delicate it is. And we also understand why that is now. But the reason is because, and I have a lot more slides in another talk about this, but not here. The whole reason why carbon gets sequestered in forests at all, for the most part, the biggest reservoir of carbon in forests is in the soils. And microflora and fungi are the things that mediate that sequestration. But you need the right kind of microflora, and you need the right fungi population. And if you disturb them, they're in competition with a bunch of other flora that'll move in and start respirating there instead. And if you do that, you can upset the sequestration. There are areas, of course, of reservoir in the biomass of the forest, in the wood and the downed wood and so forth, and then, of course, in the leaves. But if you stack the amount of sequestration that you get from like leaves to biomass in trees to soils, about 75% is in the soil in an old growth forest, about 25% is the woody biomass, including felled trees, and about a few percent are in the leaves themselves, on average, because of the, those that get sequestered and it's given up, and that's done on the course of months. The woody biomass persists for decades to a century, and then the soil carbon persists for centuries to a millennium or more. And so that's the scale of the reservoirs. So it turns out that if you do the calculations, and there are a number of estimates here for old and young growth forests, young being just not an old growth forest. An old growth forest at best sequesters about 2 metric tons of carbon per acre per year. At a young growth forest, there's about 1. And that's about that. And there are other estimates, as little as 0.23 perhaps, 230 kilograms of carbon per acre per year. And it's a little complicated. It depends on the context of the young growth forest, for example. And it also depends on the context of the old growth forest. So old growth forest, as I said, needs to be undisturbed. If, for example, for some reason, there's tree falls in that forest, and people want to go in there and clear out that tree fall and the brush associated with it, that's enough to shut it down. That's enough to shut down the sequestration. Now, understand what shutting down means, and this affects the young growth forest. Trees respirate, they release carbon dioxide. So there's this balance of how much they and the soils are giving up and how much they're taking in. And to shut it down means that those are in balance. So the forest is giving up as much as it's taking in, so it's sequestering nothing. Carbon in the soil has to stay isolated. And that requires a whole ecosystem on the top, including the wood down trees, to be intact in order for that stuff to stay there and the flora not to change. If the flora do change, a lot of microbes find that carbon in the soil and they basically say, yum, that's, you know, food to respirate, and you get carbon dioxide released from that reservoir of carbon in the soil. And that's the problem. Young growth forest, like I said, it depends on the context. If you had an old growth forest and you felled it and you used it for agriculture for a while, and then you regrew a young growth forest, it depends on the time gap that the stuff was in agriculture. But basically, during the time it was in agriculture, because there were no trees, all the carbon reserve in the soils, certainly true of eastern forests in the United States, when the trees were cut down in colonial times for agriculture, all that carbon gets respirated and released back into the atmosphere. So if you start with a young growth forest that's regrowing on top of this, it depends how far along the process this is. You can have a young growth forest that's a carbon contributor, because basically that flora in the soils has not been reestablished, and it's continuing to respirate, and it's out, you know, the rate of acid respiration is outpacing anything that the young growth forest comes down. Interestingly enough, for the northern New England, there was one set of calculations, probably by the U.S. Forest Service, I think, but don't quote me. I think that's right. I can look up that reference, that showed that if you want to sequester carbon from forests, particularly the woody biomass on the top, because if it falls, it eventually decomposes on decades to a century. One of the best things you can do is to figure out how to build buildings more out of wood and harvest this stuff. And there's going to be some loss from that, so it won't be 100%. But if you can put it in buildings and the buildings can last for a couple of centuries, that's actually a win to do that. Don't know about the proposals there. Now, as I said, thinning of old growth forests suffices to shut carbon sequestration down, and also clearing down trees turns an old growth forest into a young growth forest, at least in the vicinity of the clearing. This slide shows you a picture of in the Fisher Street Forest on the Norfolk Agricultural School campus. There was a tree fall there that happened due to a storm just a week or two back, and people had gone in there, students I believe, went in there and started clearing out some of the stuff because it fell on top of trails and things and blocked the trails. So my wife Claire and I went there the Sunday back and actually took some pictures of these things. And this is one of the larger trees that is down, and I was interested in counting rings. So that thing's about 60 years old. So that's definitely still a long way from being a young old growth forest. Also, that forest is in transition. Again, something I don't have time to talk. There's a sequence that forests go through in terms of species. What species come first, and then so typically it goes, there are conifers that start out after initial small trees and stuff, and then eventually the conifers get displaced by other deciduous hardwood trees, and this forest is very clearly in transition. All right, now let's talk about electricity. So this is a chart that shows production of electricity and its sources over time in Massachusetts. Wind and solar are minor. You can see that coal was a much bigger part of our production a long time, and that's gone down a bunch. Nuclear was up, and now it's diminishing, and solar is growing. But the biggest message is that the largest piece of electricity production in Massachusetts continues to be, or has grown to be, natural gas, 64%. And it's notable that the Walpole Greens, as I understand it, was founded to oppose a natural gas pipeline that, if I recall properly, in addition to whatever being the badness that natural gas pipelines do in general, this particular one, if something happened to it, would threaten the Walpole aquifer, and that would be bad for drinking water. But the take-up of solar and wind is slow, and this is a problem, particularly for a law that Massachusetts has called the Global Warming Solutions Act, which says that we need to be putting out 20% of 1990 emissions by the year 2050. And the Baker administration and its EAA will be talking about this more in mid-December. There's a long way to go. The slide covers nothing about transport or heating, but the solution here, as in most places, is to electrify everything. And that just means that the demand for electricity is going to be higher in the future, powering EVs and having electric source heat pumps and things for heating. So if they do that, if they succeed in having regulations, and if Massachusetts succeeds in doing that, the only reason why I say they is I'm very committed to this, but I'm not going to be around. If they succeed in doing that, he basically, who controls the cheapest electricity in that world where everything is electrified, essentially controls everything. Now, why don't we have more solar? Well, we do. We have like 80,000 homes in Massachusetts that have solar, and there's an increasing number of solar PV farms, utility farms, utility scale so-called. But there's been a lot of incentives to put photovoltaic on roofs for 8 years at least, and those incentives are going away now. Part of the reason for that is because the cost of solar PV is so inexpensive now that there should be enough monetary incentive simply to have the avoided cost of having to pay the extra money to power your house for electricity using something other than solar. And that's part of the rationale. And the other part is, I mean, it's been raised about having more incentives, but people don't respond to that. It's not, their behavior is not elastic. And this is a typical example. This is Westwood, set in Westwood, recent photograph. There's a house there. It's a relatively small house. There's 39 panels on it. And there are 2 large houses to either side, which have plenty of solar exposure and not a single panel. And they are paying for electricity. They are paying way more than they need to. And nonetheless, nobody wants these in this case, nobody wants to invest in the solar to pay for having cheaper electricity. And this is a rule. In fact, you'll find that by and large, if you go to the larger homes, you won't see any PV on the roof. And so people who suggest, say, let's not build a utility solar plant in Norfolk or wherever, put it someplace else, put it on roofs and things. This is one of the reasons why that doesn't work, is because people don't do it, whether it's businesses or homes. They just don't, even with incentives. They don't do it. They don't see that. So that's a problem. Obviously, everyone, big homes or not, uses electricity, and those fossil fuel plants are generally located in towns which have household incomes that are a fraction of the household incomes of wealthy suburbs. I mean, they use electricity too, but still. So those are some of the names of the towns, and they're the median household incomes, the respective household incomes, and those are all expressed as a fraction of the household income in median household income in the Westwood. These plants produce airborne and water pollution, harming the families and children there. People could argue harming families and children everywhere. And the people there have beautiful views of belching smokestacks. So my view is that fair is fair. It's time for people to take responsibility for the energy they consume, particularly now that it can be generated in a quiet and clean manner. I'll insert one of the questions that came up. There's an emphasis, why do we have to put it in Norfolk on the area proposed by Norfolk County? Why not someplace else? Well, what you're saying essentially is, what that's saying essentially is that somebody else's forest and land is less valuable than yours. And that takes a lot of gumption. So here is a view of the proposed Fisher ground mount plant in the middle of the forest. It occupies a bunch of cleared space. It's located some 200 feet from some homes. And I don't want to focus necessarily on this plant, but I just want to focus about these developments to the north. So that's a close-up of those developments, courtesy of Google Earth. And those are big homes. Some have pools. And if you look at them, some these up here have plenty of sun exposure on them. And nowhere here is there a sign of a solar panel. If you look to the east, the homes are smaller for the most part, not entirely. The homes are smaller, but in this view, again, from a Google Earth, you can see there are 3 homes that do have solar panels, and they're marked. But it isn't entirely true that large homes don't have solar panels, but they're rare. And if you're in this business of talking about solar and stuff, people who have these. There's one gentleman, Dave Green, and I know he doesn't mind his name being used because he promotes energy efficiency as a sideline. And he has a big home in Dover, and he has panels everywhere. Believe it or not, this is a home just off North Street in Walpole. I believe it's in Walpole. I don't know where the town lines are. It would be in Westwood, which would make it no less remarkable. And it sports some pretty serious solar arrays. These are vertical. These are not like the proposed arrays at the North Street or Fisher Street sites. These are stand up and can be, at least a couple of them can be seen from North Street itself. This is near Old North Street. And they've got, 4 of them. And I believe that's a propane tank. So, it's not, I'm sure this individual is not doing it necessarily for climate reasons. It's just that it's cheaper. And, the other thing is, of course, to note, well, a lot of the signs on North Street talk about, we want to maintain the character of North Street and that kind of stuff, and again, solar farms. Well, you got one. It's here. It's not as big, but it's here. So wanted to point that out. Again, this is a case of a big house, understands the economics, went off and put these solar panels. The advantage of having solar panels, by the way, that are stacked higher is that you need less land area. You get more oomph out of them. The disadvantage is, and the other advantage is they shed snow better. The disadvantage is because they're taller, they have more wind loading, so the structure has to be a little stronger. But they need less land area, so that's a thought. Okay, so Eversource knows about how much carbon dioxide is emitted to produce their electrical power, and it's like 0.112 if I recall. Let me just check, make sure I'm not. Yes, 0.112 tons of carbon per megawatt hour for Eversource electricity. So if you basically know how much carbon a forest sequesters, we said that it was 1 to 2 tons per acre per year. And you can convert that into the comparable number of Eversource megawatt hours by simply, figuring out by saying that if you have 1 to 2 tons of carbon per acre per year, you can divide that by 0.112 and get how many megawatt hours per acre per year, essentially equivalent sequestered carbon. Now, the Fisher Street project is expected from just general area estimates to produce about 200 megawatts per acre per year. So therefore, you can take that megawatts per acre per year sequestered carbon and figure out how long does a Fisher Street or a North Street, well, North Street isn't going to sequester carbon because there are no trees, but Fisher Street will essentially save you, or how many days does it have to operate before it saves you the comparable same amount of forest stand sequestration. This is what the numbers come out with for old growth and young growth forests at various estimates. I won't go into this. This is basically included to sort of bound it in case you wanted to include things like biofuels. Eversource produces 2 sets of numbers. One, the generation that they do in Massachusetts, which is only generated with fossil fuels. And this is all fuels, including renewables. So it's a little funny because some of this is not generating any carbon dioxide, but this one also doesn't include biofuels. This one does. So if you want to bound 16 So 27 to 51, 4 to 8 gives you an idea of the range. So essentially, from a carbon sequestration perspective, there's no contest. Forests do other things, and I'll talk about that later. It's not necessary that that land that solar PV is set on is used only for generating solar PV. I mean, you can grow pollinators or pollinating plants all around it to help pollinators out. They don't require tending in terms of cutting back the growth. That's often done using, they don't use pesticides, they use goats, in some cases, I suppose, tractors, but the goats are pretty handy. This is another case where a solar farm is being used to grow crops underneath. This is called agrivoltaics. This is a test site that the University of Massachusetts at Amherst runs. And in fact, some crops grow better under panels than they do in open sun. So it's also possible to put solar panels on ponds or lakes to some degree. I know China is doing this in a big way because it's land that nobody contests, and they have rarity of land in places. It's tougher on oceans. So you can use that land for other things as well. To do agrivoltaics, the farmers have to be trained in that practice because it's not quite the same as raising other kinds of crops. But this is a growing area, and there are a number of sites in Massachusetts and also up in Michigan. I've seen, I think if you just basically key in agrivoltaics in Google, you'll bring these things up and you can have a look at them.
Hi, how can I help?
That was Google. Thought I was asking for help. Okay. Now, the Commonwealth has this Global Warming Solution Act, which is a pretty good thing. And there's an executive order from Governor Baker called EO 569 that implements that. Originally, the reduction in emissions was supposed to come from electrification and converting electricity generation almost completely to zero carbon sources. And that's still the overall plan. The original package was thought to be wind plus solar plus hydropower development. So, and when I said wind, we included land-based wind as well as offshore. And solar was supposed to be, well, not only just roofs on houses, but big solar farms in places, particularly out west and western Massachusetts. And hydropower, principally drawn from Quebec and New York State. Now, land wind is not developed as much as sought, except in a couple of places due to opposition. Indeed, 2 wind turbines in Falmouth are being ordered to be taken down due to a lawsuit that was successfully filed by some opponents. As I said, rooftop solar has developed in Massachusetts, 80,000 homes, and it's considered by ISO New England a useful and important energy source. In order to get anywhere with this, the original plan demands utility scale solar, and there isn't enough land area. There's not enough land area in Massachusetts on other sites to be able to do this. And I'm going to drop out of the stop share for a minute and go to my screen. So this is a study that was done in 2019 called Solar Land Use Trends in Massachusetts. And I did not present this on last Monday, so this is all new to the group. So in 2019, what they found in terms of a summary was that 4,100 acres, all open space, has been used for solar development. That's 0.13%. That commercial development presents a far greater risk to open space than solar does. In contrast to the 4,100 acres, between 2001 and 2016, there was 74,000 acres were seized for commercial non-solar development. 95% of all developed open space where solar is considered development. Commercial development is responsible for nearly all, 96% of forest loss. By contrast, only 0.08% of total forest area in Massachusetts was converted to solar development. And with proper tactics, ground-mounted solar has a net positive impact on farmland preservation. The energy goals will require more solar than rooftops and brownfields can provide. 3/4 of all rooftops in Massachusetts are not suitable for solar for various reasons, ranging from shade, structural issues, and lease complications. As well as I would point out that the many towns like Westwood have, and I guess Walpole, but I won't speak to that. I'll let Phil do that. In Westwood, there are severe bylaw restrictions on ground-mounted solar properties, which I think is wrong. There are no such restrictions in Dover, conservative Dover. And 40%, yeah. Massachusetts is a national leader, but there just aren't that many brownfields. But it has, of all the brownfields that we have 40% of all brownfield solar. Sorry, let's rephrase that. Of all the brownfield solar in the United States, Massachusetts hosts 40% of it. So it's really made a big progress on brownfields already. So that, you know, if essentially, if according to their analysis, if all of the additional 800 megawatts of ground-mounted solar projected to be built under Smart 1 were built in forests, solar would still utilize less than 1/4 of 1% of forested land in Massachusetts. Part of that is there are complications there, and we haven't seen this. That's Smart 1, and that's generally talking about public land, but most of the forests in Massachusetts are privately owned. So, and part of the irony is that there have been farmers out west in Massachusetts who are proposing to mount solar farms on cleared land, cleared property that they have. And that's their own private property. And they still run into a lot of opposition. And, you know, I don't know, but, you know, certainly it seems that if it's property and that doesn't have trees on it, they want to put solar farms in it. I don't know what the opposition is about. Okay, so going back to our presentation here. So the upshot of this is that if you want to do this, and if you can't build more solar, utility scale solar farms, and you can't build land-based wind. The other two areas where you still have sources of power are hydropower from Quebec and offshore wind. And the direction where the EEA of the present administration in Massachusetts is going is that they want to double these sources. They want to double the amount of capacity that they're getting for offshore wind, and they want to double or triple the amount of power from Quebec. So my understanding of Quebec hydropower right now is that they have one dam that they're intending to divert to supply Massachusetts energy, and they're building two others. And any single one of these dams basically takes out hundreds of square miles of forest because it floods it. Moreover, that power has to come to Massachusetts in some way. And there was a proposal called the Northern Pass that was supposed to snake down through New Hampshire that was rejected by the residents of New Hampshire. There was an attempt to reject a similar path in Maine that was defeated on technicalities, and that's the current proposal. The residents are mounting a second attempt referendum to build it, but right now it's a go. And so the updated plan is supposed to be shown out by EEA in December, and one wonders what happens if Maine blocks their development. So that's where we are. That's Orsted plant. So there's a lot of unhappiness by a lot of people in Maine, including environmentalists, about this. And Nick Bennett is a staff scientist at the National Resource Council of Maine. he summarized a view with which I agree, and he says, quote, part of the problem is here that Massachusetts had been real slackers in terms of building wind and utility scale solar in the state. They still need to build more onshore and offshore wind, as well as utility scale solar, and stop exporting responsibility for generating their own clean energy to other people. Okay, thinking big for a moment, there are potentially other options. There is a company called NewScale, and there are actually a couple of others, which is proposing to develop these small modular reactors that are, safe because they're fueling and such. And, what you would do is you'd take two of these, drop them in Norfolk County, and power all of Norfolk County with them. They relatively speaking, they don't require a lot of land area. The base load, you can put them out of sight if you want. And that needing two to power Norfolk County, even if you have EVs and air source heat pumps, that would be the deal. And the hope was that, in contrast, existing nuclear power plants, which are horrifically expensive to build and have a feature which I'll talk about in a couple of slides, these would be relatively economical. So unfortunately, that promise so far is not doing well. Utah wanted to build 12 modular reactors from NewScale. And just this past week or so, that project has been delayed by 3 years and has been increased in price by 50%. So that's a concern, and it suggests, I understand the NewScale technology is new. They have to get bugs out, but unfortunately, that has been the story of nuclear power since its very beginning. Normally, if you have a technology or a device, you would expect that as you build it, once you build a lot of these things, and then you build 100 more, at the end of the 100th one, you would think that that copy that you're building is cheaper than those first ones that you built, because you know what you're doing, and you have sort of the advantages of replication scale. And that has not been the case for conventional nuclear power. The idea of the small modular concept was that it could be the case. And whether they're able to turn that around, I don't know. We're kind of running out of time, and that money might be better spent in other directions. By the way, this chart that shows the costs, I should say something. This includes France, which is a big user of nuclear power. And it's also been corrected for inflations of cost due to additional safety and environmental requirements. So this is not the actual cost that you would see, the nameplate cost that was expended to take care of those regulations. This includes the adjusted version of that, and it's still negative. In contrast, if you compare the cost of wind and solar electricity, it's exponentially plummeting. It's completely flipped in the other direction. And this reflects that, okay? So this is looking forward a little bit, but the people that project this have actually saw the decrease in wind and solar costs from the beginning of the decade. Back in 2010, there were a lot of naysayers about this stuff. And it turns out they were proven wrong. In fact, it's a funny thing. Excuse me for a second. It's a funny thing. All the standard sources about the cost of energy, whether it's the U.S. Energy Information Administration or the international counterpart, IEA, all basically do something that could be called driving, looking in the rearview mirror on these things. They basically look at what costs have been over the last 10 to 15 years, fit something to that, and then project them out. And they've had to repeatedly revise their estimates doing that, embarrassingly so, rather than looking at technological projections and stuff. And the people who were able to look forward to these, there's some big names there too, McKinsey. There's a lot of humorous history about why McKinsey is doing that now. they were able to see what this was going to. So here are a couple of hard-hitting facts about cost of wind and solar energy, with or without batteries. By 2030, the cost of construction of wind and solar will be less than the cost of operation of conventional electricity sources. So that's construction versus operation, not construction versus construction. So this would suggest that, just looking at that, why would someone get their electrical energy from a conventional natural gas source if you could just divert some of the cost of buying it and build wind and solar and still come out ahead? Because once you build wind and solar, they just generate electricity at a low price forever. I mean, it's not entirely true. If you do offshore wind, you have to maintain these things, and they're more expensive than having onshore wind turbines. And because there's something spinning in a rotor and that kind of stuff, in general, wind is more expensive, slightly more expensive to maintain than solar. Down the road, it is expected that solar will, in fact, eclipse wind in terms of just sheer out efficiency of generation, but not there yet. And there's no reason why you use it. You can think about wind as being another kind of solar energy anyway, if you want, because that's why wind blows. But that's one fact, okay? Good enough as it is. Here's the other one. Transmission costs, largely because we have an old grid that's hasn't been updated in forever. And even when the DPU wanted to pay Eversource a couple of years back to update the grid and gave them money to do so, they didn't use the money for that. In fact, they were sued by Attorney General Healy. Unfortunately, she lost because they didn't use the money in her mind properly. The cost of transmission will continue to climb. And it's what, 3 cents per kilowatt hour here. Notice back here on the previous chart, the generation cost in 2030 is like 2 cents per kilowatt hour for natural gas. But the transmission cost in 2030 is expected to be close to 6 cents per kilowatt hour. Well, I mean, look at this. Your construction of wind and solar, not operation, which is a fraction of that. Construction is 1 cent per kilowatt hour, and transmission here is 6 cents per kilowatt hour. What business person in their right mind would build a facility and get their electricity from the grid? I mean, starting out, before nothing else, you have to pay for transmission, and that's 6 cents per kilowatt hour. Moreover, at this rate, if they're going to charge you 6 cents per kilowatt hour, particularly if they get rid of net metering, why would a homeowner have anything to do with the grid? Forget the net metering. You're going to max out what you can in terms of generation of electrical energy and get batteries and have nothing to do with the grid, because why should you pay for that transmission cost? And they're going to want, that's why they want to get rid of net metering, is because they want to assign to people who are using photovoltaics and pushing the power back to the grid the cost of that transmission. And all that, if they get rid of it, all they're doing is incentivizing homeowners to abandon the grid and hoard electrons. And I mean, not hoarding electrons actually does a lot of services for the grid. But if this is where it's going to go, that's what's going to be the economic choice. And I'm suggesting that, this is what's going to change everything. And it's not that far away. Intermittency, of course, is a problem. It's an issue that comes up with nuclear, not nuclear power, solar and wind energy and stuff like that. And that is often brought up about why you continue to need things like peaker plants for gas and why you might need nuclear and that kind of thing. It turns out we know how to solve that now, and it's counterintuitive. It's like what you do is, if you need to supply all the power that you need for EVs, heat pumps, everything else. If that's one unit, what you do is you build almost 4 units of generation. and then you install whatever you need to give you 40 to 90 hours of battery storage. And if you do that, you have enough socked away and enough capacity so that, if it's a really, really cloudy, dark day and the sun blinks out for just a minute, you have so much extra generating capacity that even in a short time, you can generate a whopping amount of electrical energy to stash in the batteries again. Ditto with wind. Also, there's another thing, at least in New England. So wind and solar are anti-correlated for the most part, meaning if it's stormy, okay, you don't have a lot of sun, you tend to have a lot more wind because, well, it's a storm. Similarly, although it's not universally true, late in the day, you tend to get a lot of wind generation when once the sun starts to go down and you start to get air masses readjusting because things are cooling down. Indeed, Texas, when ERCOT built its first zero carbon facilities, deliberately took advantage of the fact that there are winds to the west of them that blow up late in the day. And there's plenty of solar generation, not a lot of wind inland during the day. And then they have another set of winds that are in the early morning along the Gulf Coast. And they basically situated wind turbines both along the coast and up into the west. And so the midday generation was handled by solar. Morning was handled by the wind turbines near the Gulf Coast. And the late afternoon into the early evening hours generation was handled by the wind turbines out to the west. So that's how you play this game. You need to install these things where they need to be and where they work for doing the generation. I'm going to be teaching a course, I hope, it's in the works, by Zoom on using this book by Mark Jacobson. And he and his team at Stanford and elsewhere have for many years put together a plan for how to decarbonize 139 countries in the world, 100% using wind, water, solar, and storage only. No nuclear, no natural gas, not anything else. And there's a book about this. I followed their work for a long time, and the book is excellent. And I'll be teaching a course based on that kind of preview. So a lot of people have worked hard to protest fossil fuels, but it's clear also that we need energy. And if it isn't natural gas, remember the chart about natural gas and electricity in Massachusetts, it has to be something. There's also a direct conflict between some of the Global Warming Solution Act and some national sentiments regarding. There's a lot in some corners of the nation. There's a lot of push to continue to support natural gas. So there may be little help from there in terms of the incentives for natural gas. The basic point is that I think that you don't really need them that much. The fact of the matter is that zero carbon energy is cheaper. It's at price competitive now, and as you go through the decade of the 2020s, it's going to get cheaper still, and then it's going to be astonishingly cheaper at the end. And batteries are going to have a price break in 2024. And once they have that, you'll see cost of EVs come down a lot. You'll see battery storage for homes come down a lot. And so I think that's where things will go and need to go. So thank you for listening to this. This is picture is a solar array at Walt Disney World. This one consists of 500,000 panels. I haven't counted them. I take the word for it. Disney World is intending to posture itself so it's completely powered by zero carbon energy. It meets goals set by the Walt Disney Company on themselves and their contractors. And they're planning to build another one like this. Note, they needed to cut down trees. And of course, this property is sort of owned by Disney. But I got to tell you, this is an example of what's coming. I mean, if you had a company like Medtronic or something, which in 2030 wanted to generate all their electricity independent of the grid because it's 6 times cheaper and they need it to land it to build it on. What do you think that they would offer for a couple of forests? I mean, you know, offer Norfolk County $200 million or something, because it'll pay for itself. You know, that's the world that's coming. And this is why I started out saying about how if you build solar arrays now, you're controlling the generation, you're making the zero carbon generation available now. You don't have to necessarily feed that to a grid forever, to the Eversource or whoever's grid forever. You could consider setting up a microgrid that would power just Norfolk County, say, if you do this, and you would remain as attractive to real estate and residential developers as ever, and business. And there wouldn't be this all of a sudden, you know, Amazon flying in, building a warehouse. They are building one in Norwood, by the way, and saying, oh yeah, well, we want zero carbon energy and this is what we'll pay to get it. And that's why I say that economic thing is what's important. Climate change is important too. And it's important for us to do our share on climate change, and that needs to be the focus there. But people are reluctant to take actions on those measures too, even when it's not in their interest to not do so. A little, you know, fact about climate change and its effect on places like Walpole and Westwood and stuff like that. Right now, not in the future, right now, there's a 1 in 50 probability of having an 8-inch rain event in 24 hours each year. So that is, any given year, you have a 1 in 50 chance of getting one day where you have 8 inches of rain in 24 hours. There is no stormwater management system, which is generally built to handle 2-3 inches a year, maybe 4 tops of rain in 24 hours, that can handle an 8-inch rain event. And because of the warming on the planet, in this area, the amount of bursts that you have, the probability of bursts is going to go up because the air is warmer, so it holds more water, and so it drives bigger storms. In fact, winds meteorologists in this area will tell you this. I learned this at the Southern New England Meteorological Conference, that winds over the past 20 years in here along the Atlantic coast have increased 15% in strength on average. That is going to, that probably, it's 1 in 50 now, it's going to go down to 1 in 25 and eventually lower. And the fact of the matter is, it's, you know, here's this bad event, right? So it's 1 in 50 or 1 in 25, and you keep flipping a coin. In this case, say it's a 25-sided coin, it becomes 1 in 25. Every year I have a 25-sided coin. Actually, I have a die, not a coin, a die. I actually have a die that has a bunch of sides like that on it. Anyway, so, and every year there's a 1 in 25 chance of landing on the one side that's bad, the 8-inch rain event. Well, if you keep repeating this, you know, if you basically do this 10 times in a row for 10 years, and you figure out, well, what's the probability of having at least 1 year there where you have one or more times that there's an 8-inch and 24-hour rain event? And, you know, you do the calculation, it's a binomial. So, you know, it's, you know, the integration of, if it's just one, it's 10 choose one of the thing. So the probability is a lot more than 1 in 25. Eventually, if you let this wrong enough, it's sure to happen. And that's independent of the fact that the risk every year is increasing, which it will be because of the warming temperature. So it's pretty clear to me that not a lot of people are thinking about what are the repercussions of getting 8 inches of rain in 24 hours, in certainly not in Westwood. And they really should, because Westwood, I can't speak to Walpole, but Westwood is built on wetlands. And there's a lot of badness that could happen from bigger rain events like that. And this isn't necessarily a hurricane. It could be, this isn't necessarily a hurricane. It could be lots of things. So that's an example of where you need to think about the impacts of climate change and warming going down the road. And then there's our friend, the woolly adelgid. The weather deluge is a new problem. It was imported accidentally, probably on ornamentals from Japan. But it was imported actually some time ago. I think it was imported in, if I recall, I'm not sure, New Jersey or something like that. And if it weren't for the fact that our winters are warmer now, you wouldn't have a problem with it. Because if you have like, I don't know what I don't remember exactly what the critical temperature is, but if you have like a 20-day run of below 0 Fahrenheit temperatures, like 10 degrees below, it doesn't survive. That's because the adelgid has a funny life cycle where it actually does reproduction in the wintertime. So the only reason why that thing is affecting forests and stuff is because our winters are warmer. And it is the quintessential example of a creature that has undergone a phenological change and is expanding by its original place of dominance into other areas that it can thrive in. And there's more available to us. I mean, there will be more things like that come. Okay, let me ask a couple of questions kind of related to this. There was a question posed during the talk about what the impact of additional warming is on solar panel production going forward. Decent question. And I gave an answer during the talk, but it wasn't very satisfactory to me. So I looked it up since that time. And here's the crisp answer. Overall, for all solar production in the world, it's expected that by 2100, there'll be a 10% variation beyond design. And that's just from weather and such. In New England, it's actually expected, it will go down some, and also in the world, it will go down. The reason why it goes down is because if the world is at higher temperatures, solar panels don't operate as efficiently at higher temperatures than they do at cooler ones. Also, however, and that will be true in New England, but in New England, there's actually expected to be an increase in the amount of solar production, even if there is cloudiness. And the specific reason for that is that over the next, say, through 2100, by the end of this century, you're expected to have a very few days where you have snow cover that lasts for more than 2 days. Indeed, by the end of this, there are charts from the Northeast Climate Science Center that shows this, that by the end of the century, as things continue now, we are going to have the climate of Georgia. And so that will facilitate production of solar panels. And I can't seem to, let's see, what other questions were there? Well, there was a lot of concern in one case about why do you have to build it here and why not someplace else? And I've addressed some of those. There's concern about loss of trails and natural place in which to walk in, and I understand that. But realistically, realistically, so here's a view again. I think it's Google Maps, not Google Earth, from higher up, that shows the area. There's the Fisher Street generation, North Street generation. So the North Street farm is, I think, someplace in here, in a depression, but that's the general area of the Fisher Street forest. And Rocky Woods, Noon Hill, Cedar River, Indian Trail, Walpole Trails, the Moose Hill Wildlife Sanctuary. There are a lot of places to go walk in around us. And also, per that comment from the Community Solar Access people, this stuff, okay, in Norwood, in Walpole, in Medfield, this stuff used to be forest, this development. And even in Westwood, if you look back, in the 1950s, 1960s, 1970s and stuff, of what Westwood looked like, it was forested. A lot of that development didn't happen. So, I can understand being concerned about open spaces and trees and such like that, but I think picking on solar development is, well, at the very least, it's a waste of personal energy, whereas the concern should be put to have a bigger trade-off. Conversion should be put at trying to restrict development. And the other thing I suspect, and I did not say this Monday, but I've thought about this for a while. And the other thing I suspect is one of the things that the community solar access people point out is that if you develop a parcel for solar energy, that's a typically 20, 30-year time frame that you're investing in. I wonder to what degree opposition of a solar project in Norfolk County or anywhere like this is because there are people who are developers or who are make their money working for developers who are concerned about the possibility of a large parcel like that being taken out of circulation effectively for 20 or 30 years. And they feel that perhaps that parcel could be turned into condos or something. And there's a lot of self-interest there, peculiar self-interest that doesn't benefit the general population. I'm obviously editorializing. This is only my personal perspective, all this stuff now. And that isn't what's good for developers isn't necessarily good for the county. And it's certainly not good for our kids and grandkids going on. It's good that Walpole is getting into a green community status, but as we saw in some of those big farms, big homes in some of my earlier slides, even the one with the solar panels, they still use propane. And that isn't the direction where we're going to be going in any way. That unfortunately, that I'm sure that developers may fight that. They probably will fight the idea of homes having to be completely using geothermal or air source heat pumps as well. And we'll see where that goes. But I wonder about what the incentives are for some of the opponents of the solar farm. Other ones are clearly well motivated with concern about ecosystems and ecosystem services and so forth. About that. Oh, one thing I should say about this, I didn't say this the other day. At the end of the slides, I have references that talk about all the points, most of the points that I've addressed in this talk. And you can check those things out. The last thing that I'd like to say is that about natural systems and such. Even the forests that we have here are not natural systems. They are so circumscribed and so disturbed by development all around them that the ecosystems thereabouts have been all chopped up. And the wildlife that's here has very much adapted itself to living with people, including preying on stray cats and dogs, for example. So this is by no means is this any kind of a natural landscape. It may be, well, I don't know if it's any more natural than a farm is, but a farm certainly isn't. So we're trying to preserve natural landscapes in little patches where it can be contained and sustainable, but that's not a natural landscape. The other reason, to answer the other question about why can't you just put these generation pattern things anywhere, well, one of the other reason here can be seen on this chart, and I didn't talk about this at all. The North Street PV array is located right near this line here, cutting through the woods. That's a transmission line, presumably Eversource or whatever they used to call themselves, or where the transmission company comes. So you need two things. You need a place where you can build an open space, And you also need access to be able to put that power someplace, to be able to put that power onto the grid so that it can be used. That is, of course, unless you have a microgrid for your own town or something. But nonetheless, if you're going to feed the grid, you can't just put it anywhere. And Eversource or whoever the utility is has to sign off on that because their infrastructure has to be able to handle it as you're putting that power. So that's the other reason why you can't just put it any old place. Okay, and so that's it. The last thing is ecosystem services for all kinds of ecosystems are fungible to some extent. It's not clear that if you cut down a forest and you plant a solar farm there, that you've lost all your ecosystem services. You now have a grassy field, and that provides some ecosystem services, not exactly the same ones, but there are ecosystem services there. And also the other thing that people that do this kind of stuff seriously look at is there is a price for ecosystem services, and there is now a pricing scheme. And not that I want to say that everything's reducible to dollars, it's not, but if you want to compare things, the nice thing about pricing is that, you know, it's a total ordering, what mathematicians call the total ordering. It's a one-dimensional total ordering, and it's an oversimplification. But if you want to, you know, compare things in terms of get some sense of the value of ecosystem services of forest versus fields and stuff like that, that's a place in the literature that you can go to, and it will address that. So thank you for listening. Probably went on long, I don't know, I imagine so. But then presumably if you're watching this on YouTube, you have the time and you can start and stop it all you want. So thank you for all you're doing. Hope this works out. If it doesn't work out, you know, my perspective is there'll be other choices someplace else. I'm not going to be all upset if it doesn't work out, that kind of thing. Eventually, what will happen is that the cost of climate change will essentially be serious enough that people will start to get scared. Their options will be more limited at that time to be able to do counteract that, but you can't make people see what they don't want to see. And then the last thing is, most notably, the cost of energy will go in the direction, as I say, and that will have its consequences. And you know, when people make investments, they aren't necessarily the wisest investors, and so you shouldn't beat yourself up that you didn't do enough to make this thing happen. There will be consequences if people don't make the right choices, I'm sure, and that's all there is to it. And we go on and we try to solve this problem some other way. I should say an area that I'm going into right now, it's kind of interesting. It is so I'm a member of the Unitarian Universalist Church, First Parish in Needham, and we have a lot of liberal views, I would say, to represent the congregation. We're open to everybody, however. Liberal views, I don't consider LGBTQ rights particularly liberal, but some people might. Anyway, and people there have been trying to get things done on advancing zero carbon energy and so forth. I think it may be that the tactics that I and some of the others have been pursuing over the past 5 years or longer, 10 years maybe, are not as effective as they might have been. And I think pursuing economic motivations like this might be more. In any case, one of the things I'm excited about is reading into the results of the current election. I'm very obviously glad that the outcome of the presidential election was what it was. But you can't go away from this without understanding that there are a lot of people in the world that if we want to do anything big, we're going to need to learn how to talk to. I'm going to need to learn how to talk to. And so one of the things I'm excited about is that I've reached out to a group called the American Conservation Coalition, which is run by a very brilliant young Republican, Benji Backer, who founded this thing. And he founded it because there are many young Republicans who are really concerned about climate change, and they consider their leadership's lack of action on it to be a travesty. And the American Conservation Coalition is making an attempt to advance solutions towards climate change, using market-based approaches and arguing that these are completely compatible with other conservative values. And I see this as a wonderful opportunity for people who have historically been liberal and have perspectives like I do, to have something in common to talk about, have something in common to suppose reach across the aisle, but reach across the community and have a conversation where we can work together on something and sort of understand each other better. And I think there's nothing better than energy. I was partly moved to do this both because I want to get progress. I'm a climate hawk. Anybody, Republican or Democrat, who has a cogent, workable plan to work things on climate, I will vote for them. Period. That's it. Because climate, there's nothing bigger for environmental concerns than fixing climate. You got to fix climate, and you got to do it soon. That's absolutely true. That's my personal viewpoint. Claire and I took a ride in our Tesla up to Ithaca, New York, visiting my older son there. And we drove on a stretch of road. I think it's Route 122. It connects Interstate 88 with basically Ithaca, Interstate 79 that goes to Ithaca. And it goes through a town called Bainbridge in upstate New York. I used to live in upstate New York. And all along this road, there are all these basically sad, failed farms that basically have not had any kind of success, and they've been in hard times for 20 years, maybe. 201, they supported the Republican presidential candidate. And that and the work of a couple of economists at MIT, Duflo and Beneri, suggests to me that the only reason why this happens is because there are some people who have been so left out of the economic conditions, not just in inner cities and places like that, but all around the rural areas, are desperate to do something to improve their situation. And I'm hoping that energy everywhere can be the thing that will help them become that and help fix that problem. I don't care who they vote for. It's clear that there are a lot of people suffering there. And that is something I'm hoping that work with the American Conservation Coalition and trying to get some more progressive groups to see that working with them is a great idea. I think that might be a place for some progress. So thank you again for listening, including my sermon at the end. Hopefully, if you got bored with it, you cut it off. I'm sure you did. So thank you very much. If you have any additional questions, reach out to me. You can contact me either by the YouTube, or you can look me up on the web. It's hard to miss me or my blog. Thank you.